Comparison tests, including the ratio and root tests. We begin with a notational convenience. The sum of a sub k represents the sum as k goes from k0 to infinity of a sub k for any starting index k0. We do this because we are only concerned here with the question of whether a series converges or diverges, and the starting index k0 is irrelevant to that question. In fact, changing any finite number of terms in any series has no effect upon whether the series converges or not. What we know so far. We've learned that the following basic series converge. The geometric series, the sum of x to the kth power, converges if the absolute value of x is less than 1. Also, a p-series, the sum of 1 over k to the pth power, converges if p is greater than 1. And here are some basic series that diverge. A p-series, the sum of 1 over k to the pth power, diverges if p is less than or equal to 1. And any series whose terms do not approach 0 as k goes to infinity will diverge. Now let's describe a basic comparison test. Suppose that a sub k is greater than or equal to 0 and b sub k is greater than or equal to a sub k for all sufficiently large k. If the sum of b sub k converges, then so does the sum of a sub k. If the sum of a sub k diverges, then so does the sum of b sub k. Comparisons with p-series can be stated as follows. The sum of a sub k converges if a sub k is between 0 and a constant c divided by k to the pth power where p is greater than 1, since we know that the sum of a constant divided by k to the p converges when p is greater than 1. Also, the sum of a sub k diverges if a sub k is greater than or equal to a positive constant c divided by k to the p where p is less than or equal to 1, since we know that a p-series with p less than or equal to 1 diverges. Applying the basic comparison test with a geometric series tells us that the sum of a sub k converges if a sub k is between 0 and a constant c times x to the k where x is strictly between 0 and 1. A comparison of the sum of a sub k to a divergent geometric series is unnecessary because for such a series the terms would not approach 0 as k goes to infinity. Now let's look at a few examples. First, let's consider the sum of k divided by k squared plus 100. What we want to do here is to estimate the kth term either from below by the kth term of a divergent series or from above by the kth term of a convergent series. The key here is the estimation of the denominator k squared plus 100. Note that k squared plus 100 is less than or equal to k squared plus k squared when k is greater than or equal to 10, so the denominator of the kth term is less than or equal to 2k squared when k is at least 10. As a result, k divided by k squared plus 100 is greater than or equal to k divided by 2k squared, which equals 1 over 2k, when k is greater than or equal to 10. Now we know that the sum of 1 over 2k diverges since it's a multiple of the harmonic series, and so we can conclude that the sum of k over k squared plus 100 diverges because the sum of 1 over 2 times k diverges, and k over k squared plus 100 is greater than or equal to 1 over 2k when k is greater than or equal to 10. Example 2. The sum of 1 over k cubed minus k squared. Let's try to get an upper estimate of the kth term in the form of a multiple of the kth term of some p-series. We'd like to somehow combine the two terms k cubed and minus k squared in the denominator into one. So let's notice that k squared will be less than or equal to any positive multiple of k cubed when k is sufficiently large. In particular, k squared will be less than or equal to k cubed over 2 when k is at least 2. Therefore, minus k squared is greater than or equal to minus k cubed over 2 when k is at least 2. And so our denominator, k cubed minus k squared, is greater than or equal to k cubed minus k cubed over 2 for k greater than or equal to 2. So, when k is greater than or equal to 2, 1 over k cubed minus k squared is less than or equal to 1 over k cubed minus k cubed over 2, which equals 2 over k cubed. So finally we conclude that our series converges because the sum of 2 over k cubed converges and 1 over k cubed minus k squared is less than or equal to 2 over k cubed for all k greater than or equal to 2. For a third example, let's look at the sum of the kth power of 7k over 8k minus 7. Here we're going to do a comparison with a geometric series. To get an estimate on the kth term, let's first observe that 7 is less than or equal to k over 2 when k is at least 14. So minus 7 is greater than or equal to minus k over 2 when k is at least 14. So 8k minus 7 is greater than or equal to 8k minus k over 2 when k is greater than or equal to 14. Therefore, when k is greater than or equal to 14, the kth term of our series is less than or equal to the kth power of 7k over 8k minus k over 2, which after simplification becomes 14/15 to the kth power. That is the kth term of a convergent geometric series, since 14/15 is between 0 and 1, and so we conclude that our series converges because the sum of 14/15 to the kth power converges, and the kth term of the series is less than or equal to 14 over 15 to the kth power when k is greater than or equal to 14. The limit comparison test is easier to apply than the basic comparison test. Let the sum of a sub k and the sum of b sub k be series with positive terms. If a sub k divided by b sub k approaches a positive limit as k goes to infinity, then the two series either both converge or both diverge. If the limit as k goes to infinity of a sub k over b sub k equals 0, and if the sum of b sub k converges, then so does the sum of a sub k. Let's note that the condition that the limit as k goes to infinity of a sub k over b sub k equals a positive number r essentially means that a sub k is approximately equal to r times b sub k for large K. Now let's look at a few examples. First, let's consider the sum of 1 over k times the square root of k squared minus 1. To find a series with which to compare, let's first note that for large K, 1 over k times the square root of k squared minus 1 is approximately equal to 1 over k times the square root of k squared, since the minus 1 under the radical will be insignificant compared to k squared. So the terms of our series are approximately equal to 1 over k squared for large K. So we'll do a limit comparison test with the series, the sum of 1 over k squared. First we divide 1 over k times the square root of k squared minus 1 by 1 over k squared, which gives us k squared over k times the square root of k squared minus 1, which, after we divide the numerator and denominator by k squared, becomes 1 over the square root of 1 minus 1 over k. The limit of this as k goes to infinity is clearly 1, and so we conclude that our series converges by the limit comparison test with the convergent p-series, the sum of 1 over k squared. Example 2. Let's determine whether the sum of the cube root of k divided by 5k plus the square root of k converges or diverges. Notice that when k is large, the square root of k is much smaller than 5k, and so the kth term here would be approximately equal to the cube root of k divided by 5k, or 1/5 times 1 over k to the 2/3 power. So we'll conduct a limit comparison test with a series whose kth term is 1 over k to the 2/3. To do this, we'll divide the kth term of our series by 1 over k to the 2/3, which amounts to multiplying by k to the 2/3, which gives us k divided by 5k plus the square root of k. Now dividing the numerator and denominator by k gives 1 over 5 plus 1 over the square root of k, which clearly converges to 1/5 as k goes to infinity. We conclude that our series diverges by the limit comparison test with the divergent p-series, the sum of 1 over k to the 2/3 power. Example 3. Consider the sum of the kth power of 2k divided by 3k minus 2. The kth term here is approximately equal to 2/3 to the kth power when k is large, so we'll use a limit comparison test with the geometric series, the sum of 2/3 to the kth power. So we divide our kth term by 2/3 to the k, which is the same as multiplying by 3/2 to the k, and combining those two factors gives us the kth power of k over k minus 2/3. This is the reciprocal of the kth power of 1 minus 2/3 divided by k. Now let's recall that the kth power of 1 plus x over k approaches e to the x as k goes to infinity. So the denominator here approaches e to the minus 2/3, and therefore the quotient approaches e to the 2/3 power. So now we conclude that our series converges by the limit comparison test with the convergent geometric series, the sum of 2/3 to the k. Comparison with geometric series. Let the sum of a sub k be a series with positive terms. If the sum of a sub k is a multiple of a geometric series, then the ratio of consecutive terms, a sub k plus 1 divided by a sub k, is constant. That's because x to the k plus 1 divided by x to the k simply equals x. If a sub k plus 1 divided by a sub k is approximately equal to rho for large K, where rho is less than 1, that is, if a sub k plus 1 divided by a sub k approaches rho as k goes to infinity, where rho is less than 1, then the terms of the series are dominated by the terms of a convergent geometric series for large K, and so the series will converge by the limit comparison test. The series used for comparison could be any geometric series, the sum of x to the k, where x is a number strictly between rho and 1. This is the idea behind what is known as the ratio test. Suppose that a sub k plus 1 divided by a sub k approaches a limit rho as k goes to infinity. Then the sum of a sub k converges if rho is less than 1 and diverges if rho is greater than 1. If rho equals 1, the test fails. In other words, if rho is equal to 1, then the series might converge or diverge. Examples. Let's determine whether the sum of k cubed over 2 to the k converges or diverges. To perform the ratio test, we look at the ratio of the k plus first term, a sub k plus 1, to the kth term, a sub k, where here a sub k plus 1 equals k plus 1 cubed over 2 to the k plus 1, and a sub k equals simply k cubed over 2 to the k. Let's rewrite this quotient as k plus 1 cubed over k cubed times 2 to the k over 2 to the k plus 1. Now 2 to the k over 2 to the k plus 1 is equal to 1/2, and so we have 1/2 times k plus 1 cubed over k cubed. K plus 1 cubed over k cubed clearly approaches 1 as k goes to infinity, and so a sub k plus 1 over a sub k approaches 1/2, which is less than 1 as k goes to infinity, and therefore we conclude that our series converges by the ratio test. Another example. Let's determine whether the sum of 2 to the k divided by 3 to the k minus 2 to the k converges or diverges. We'll use the ratio test. A sub k plus 1 divided by a sub k here equals 2 to the k plus 1 divided by 3 to the k plus 1 minus 2 to the k plus 1, all divided by 2 to the k over 3 to the k minus 2 to the k. This is equal to 2 to the k plus 1 over 2 to the k times 3 to the k minus 2 to the k divided by 3 to the k plus 1 minus 2 to the k plus 1. The first factor there is simply 2, and if we divide the numerator and denominator of the second factor by 3 to the k, we obtain 1 minus 2/3 to the k over 3 minus 2 times 2/3 to the k. And since 2/3 to the k approaches 0 as k goes to infinity, we find that a sub k plus 1 over a sub k approaches 2 times 1/3 as k goes to infinity. Since 2/3 is less than 1, we can conclude that the series converges by the ratio test. Another example. Consider the sum of 1 over the square root of k factorial. We'll use the ratio test again. For this series, a sub k plus 1 equals 1 over the square root of k plus 1 factorial, and a sub k is simply 1 over the square root of k factorial. This ratio is equal to the square root of k factorial divided by k plus 1 factorial. Now let's recall that k plus 1 factorial is equal to k plus 1 times k factorial, and therefore k factorial divided by k plus 1 factorial is simply 1 over k plus 1. So a sub k plus 1 over a sub k is equal to the square root of 1 over k plus 1, which clearly approaches 0 as k goes to infinity. Since that limit is less than 1, we conclude that the series converges by the ratio test. Now let's apply the ratio test to the sum of k squared times 2 to the k over k factorial. Here, a sub k plus 1 equals k plus 1 squared times 2 to the k plus 1 divided by k plus 1 factorial, and a sub k is simply k squared times 2 to the k divided by k factorial. We can rewrite this quotient as k plus 1 squared over k squared times 2 to the k plus 1 over 2 to the k times k factorial over k plus 1 factorial. 2 to the k plus 1 over 2 to the k is simply equal to 2. K factorial over k plus 1 factorial equals 1 over k plus 1. And so a sub k plus 1 over a sub k is equal to k plus 1 squared over k squared times 2 over k plus 1. The first factor here clearly approaches 1, and the second factor approaches 0, and so a sub k plus 1 over a sub k approaches 0 as k goes to infinity. And since that's less than 1, we conclude that the series converges by the ratio test. Another comparison with geometric series. Let the sum of a sub k be a series with positive terms. If the sum of a sub k is a multiple of a geometric series, then a sub k to the 1 over k power, that is, the kth root of a sub k, is constant. That's because x to the k raised to the 1 over k power is simply equal to x. On the other hand, if the kth root of a sub k is approximately equal to rho for large K where rho is less than 1, that is, if the limit as k goes to infinity of a sub k to the 1 over k is the number rho less than 1, then the terms of the series are dominated by the terms of a convergent geometric series for large K, and the series will converge by the limit comparison test. The series used for comparison could be any geometric series, the sum of x to the k, where x is a number strictly between rho and 1. This is the idea behind a test known as the root test. Suppose that the kth root of a sub k approaches a limit rho as k goes to infinity. Then the sum of a sub k converges if rho is less than 1 and diverges if rho is greater than 1. If rho equals 1, the test fails. Now let's look at a couple of examples of how the root test is used. Consider the sum of the kth power of k plus 5 over 2k. To perform the root test, we take the kth root of a sub k, which here is simply k plus 5 over 2k. The limit of that quantity is clearly 1/2, which is less than 1, and so the series converges by the root test. Another example. Consider the sum of k minus 1 over k, all raised to the k squared power. To perform the root test, we take the kth root of a sub k, which will be k minus 1 over k to the k squared divided by k power, or in other words, the kth power of k minus 1 over k. That's equal to the kth power of 1 minus 1 over k, which we recall approaches e to the minus 1 power as k goes to infinity. Since e to the minus 1, or 1 over e, is less than 1, we conclude that the series converges by the root test.